All right, so last time we ended, we were talking about corrections to the propagator, right? And we found that if you consider, to all orders, you can write the exact propagator, which I can't bold, so I'm going to put a hat and a squiggly line. So that's the exact propagator. And it has a form that kind of looks like the non-interacting propagator. It's got this new piece that depends on the forward momentum squared, right, that we call the self-energy. Okay? And so what we set out to do is to try to compute that self-energy to a fixed order. All right? To a fixed order, I mean something beyond leading order, so we're going to work it next to leading order, okay? In this phi cubed theory. Right? And if we apply, the conditions that the propagator has, because we don't want to screw up the conditions that the leading order propagator had. So we want to impose that this thing still has a pole at k squared equals m squared and a residue of 1. And so it leads us to two conditions that when we evaluate this guy with k squared equal to m squared, they better vanish. Right? That makes sense because we still want a pole, right, at m squared. And the other condition is that the derivative with respect to k squared evaluated at k squared equals m squared also has to vanish. All right? So what we want to do is we want to compute the self-energy. Once we have the self-energy, remember the self-energy is just the propagator with the external, it's just the propagator with the external propagator stripped off. Okay? So we want to compute the self-energy and then apply these conditions. Right? And if you remember, in our expression, we had one term that went like a k squared plus b m squared, where these guys are related to the z factors, the counter terms in our original Lagrangian. Okay, so what these two conditions are going to allow us to do is to evaluate or to compute those two counter terms. Okay. All right. So we started out with by computing. We wanted to compute the loop diagram. This guy. Okay, so this is the first order correction to the leading order propagator. All right, and so if we apply our Feynman rules, we've got, let me call the momentum coming in K. Right, this guy is L, and that makes this K plus L. Okay, and so that means that I've got K coming out. Okay, so I want to apply my Feynman rules and write down the amplitude for this thing. Okay? So it's typically, if it was a scattering amplitude, we would write IT, where T is the T matrix. Here, we're going to call this thing I. Okay, it's going to be related to the self-energy, or it's part of the self-energy, and it's going to be a function of k squared. Okay, so I have what? I've got two factors of the vertex, which I assign two factors of IG. Right? I've got two internal propagators, so that gives me two factors of 1 over I. So those i's are going to cancel each other out. And then I've got to integrate over the undetermined momentum, L here. Right? And we're going to work in d dimensions, and you'll see why in just a little bit. Okay, so now I just need to write the denominators for these guys. So the first is L squared minus M squared, and the other is L plus K squared minus M squared. Okay, so we can see that the factors of I are going to cancel out. Now what am I forgetting? Anybody? This diagram has a symmetry factor, right? Has a symmetry factor of 1/2.
Oh yeah.
2, right? So we want to divide by the symmetry factor. Okay. Okay. So that's what we got to this point last time. We noted that For D greater than or equal to 4, so for D, for 4 dimensions and up, this thing is going to be UV divergent. Okay, and so we've discussed, these UV divergent integrals before, and we've talked about how you can regularize them, make them well behaved, right? And one way that we have seen was the cutoff. The cutoff method, sometimes called the Pauli-Villars cutoff method. We're going to use a technique called dimensional regularization, which I'll just call DemReg, right? And our approach is going to be to work in D less than 4. So we'll assume that we're in some smaller number of dimensions where this integral is safe, and we'll compute it, and then we'll take the limit to whatever dimensions we want, whether it be 4, 6, or 22. Okay. All right. But the first thing we have to do is try to evaluate this integral. Right? And it's difficult, to say the least, but what we're going to do is try to use some tricks and put it in a more convenient form. Okay? We want to try to put it in a form where we can, use spherical symmetry, right? Because we know how to do, in that case, we could write this integral element, in spherical coordinates, and we'll have something that's, L squared, and we can do those integrals. Okay? And angular pieces are going to be the easy parts. So what we want to do is we're going to use a trick introduced by Feynman, where you basically combine these denominators. You have to introduce a new parameter to the calculation, a Feynman parameter, but it allows you to combine that denominator and get something that's spherically symmetric. Okay. The bad thing is that you've got this new integration that you have to do, but worry about that later on. Okay. All right, so the trick, I think I wrote it down last time, or had it on the slide last time. The trick is that you can always write the product of denominators, A and B, like this. And normally you'd be like, why the hell am I doing that? Right? Okay. All right, so the trick is we're gonna do something like this. So we're gonna introduce a new parameter. This guy's called the Feynman parameter, right? And we're gonna integrate over it from 0 to 1. Right? And I'll let you prove yourself that you can do this integration from 0 to 1, and you get 1 over AB. Okay? And you can do it several different ways. You can do it by introducing just 1, or you can introduce 2 Feynman parameters. Both, well, x, let's see, one of them from 0 to, both of them 0 to 1. And a delta function that tells you x plus y has to be 1. And then 1 over x a plus y b squared. Okay, so you can use either one of these expressions. Typically when we're computing just a 2-point function, this is going to be the most convenient one. Right? But when you get to higher orders, sometimes or when you get to more complicated loop diagrams, it's sometimes better to go with this one. Okay. All right. So let's see how it works. Okay. So we want to combine this denominator, or combine this denominator, right? So let me do this. All right, so my denominator, all right, so I'm just going to denote D as my denominator. It's this stuff, these two factors. Okay, and let me introduce the Feynman parameters. Okay. So let me introduce, I'm going to do it, I have a choice. I can multiply the first by x, or the second by x, and the other one by 1 minus x. I'm going to multiply the first by 1 minus x. So I have 1 minus x times L squared minus M squared plus x times L plus K understand what I'm doing? Just writing down the denominators right now. Okay, so then I have, let me carry out that square. L squared minus m squared plus x. And now I've got L squared plus 2L. Remember, these are four momentum, so it's a dot product. L dot k plus k squared minus m squared. All right. So far, so good. Okay, so now I see, let me group factors of L. Okay, now I can see that this piece, right, the minus x here is going to cancel off that part. Right, so I'm going to end up with L squared. And what do I have left? At first order, I've got 2x L dot k. And then I've got x k squared. And again, with the m squared, the x cancels out that minus x, so I'm left with minus m squared. Is that good? Yes? Okay. So here comes the trick. Okay, so we want something that is of the form some momentum. Let's call it Q plus it can be some other stuff. This is called constant squared. Right? We want it of that form. We want something that's spherically symmetric. Okay. All right. So what we want to do is we want to complete the square on this guy. Okay. To do that, I'm going to introduce a new momentum. I'm going to call it Q, and it's going to be defined as L plus xk. All right, so this is my new variable. Okay, so let's see how it helps us. So if I take Q squared, L squared plus 2x L dot k plus x squared k squared. And what are we trying to do? We're trying to get rid of this term, right? We want something that just goes like Q squared plus some constant stuff, okay? So what I can do is I can use, so here I have L squared plus 2x L dot k. Here I have L squared plus 2x L dot k. All right, so I can replace these two terms with Q squared minus x squared k squared. You guys haven't figured it out yet. I wait for Michael to nod and then I move on. Just kidding. All right, so the denominator, becomes Q squared minus x squared k squared plus x k squared minus m squared. So this is the stuff that's left over after I make that change. Okay, and I can make this look a little prettier. I can call it Q squared plus x times 1 minus x, k squared minus m squared. Okay, and then finally what I can do is I can define this stuff to just be some quantity, and I'm going to call it capital omega. All right, so my denominator becomes Q squared plus omega. So having done that, let's go back to our integral, which I've already erased. Let's put in what we have now. So I have I times I as function k squared. Okay. I've got g squared over 2. I've got my integral dd, and now it's an integral not over L, but we've made the change to Q. So it's d of Q, 2 pi d. And now my stuff in here is this Q squared plus omega squared 1 over. Okay? What have I forgotten? Hmm?
Symmetry.
Oh, yeah, no, symmetry
we
factors
already
there.
have that. That was the first thing I thought, but then I looked closer and said, no, we already have that.
I remember I introduced a Feynman parameter to rewrite those two denominators, right? And when I introduce the Feynman parameter, I have to integrate over that Feynman parameter. Okay, we have to integrate this thing from 0 to 1. So before you jump for joy, you're thinking, you know, we've got this problem solved. Remember, this thing is, you know, a function of x. Okay, that's where the hard work comes in. That's typically when you resort to numerical techniques, when you get it down to that point.
And we consider k as constant, yeah?
Yeah. Yeah. Okay. Yeah, it's at a fixed k. Remember, k is the incoming momentum. Okay. All right. So notice that I've commuted the x integral and the q integral, but that's fine. They do commute. Okay. So technically, I should have that dx integral inside here. Right. But they commute. Okay. So now we want to try to compute this guy. Okay. And Peskin has a quote in the book where he says, it's not difficult to do, so remember this is, you know, this is still a 4 vector, or well, it's a d, I guess d-dimensional vector, but he says it's easy to do this integral.
Mm-hmm.
The q, so you can break it up into q0, q1, q2, you know, so on and so forth. He says it's not difficult to evaluate the q0 integral as a contour integral. That just, to me, is like an oxymoron, or I don't know. Not difficult and contour integral should not be in the same sentence. And then so he says it's not difficult to do this, and then you do the rest in spherical coordinates. Right? So that's his statement, but I'm going to show you how we do that, okay? And it's through a trick that we call wick rotation. Okay, so this is one of those things that, like I said, you know, you're going to learn one time. We're going to get down to the point where we have a master formula. And so anytime you encounter one of these integrals, you can just go and, you know, pick out that master formula and apply it. It's just plug and chug. But, you know, it's good to see at least once. Okay. All right, so the point of doing this, of having to do this wick rotation, is that you notice that if I was in a normal Euclidean space, I could already do this spherical integral, right? I could already work in spherical coordinates and do this integral, right? But the problem is that we're not in Euclidean space, we're in Minkowski space, right? Where q squared is equal to q naught squared minus the 3 vector squared. Okay, so we can't use d-dimensional spherical coordinates. That's the problem. Okay. However, we can do a rotation into Euclidean space. Right? And the way we imagine that is to think of the q0 integral. Right? The q0 integral, we're integrating over all q0, right, from minus infinity to plus infinity. But there's going to be some poles in there. So let me draw. So right, if I consider the complex plane, there's going to be poles from this integration, and let me denote them like this. All right, so initially, if this is real q0, then this is imaginary q0. All right, so we're doing the integration originally along here, okay? And the idea, so how would we do this integration? We'd use the contour integral and all that stuff, right? So, as long as I can rotate this integration, as long as I don't cross over a pole, I don't screw anything up, right? So what I want to do is I want to take this integration and rotate it counterclockwise onto the imaginary axis, right? And integrate that from minus I infinity to plus I infinity. Okay, so you see what I'm doing?
What's
Hmm?
I infinity?
Well, it's just
Oh,
imaginary.
infinity.
Minus little I, the, you know, imaginary number.
I times infinity.
Yeah. Yeah. Okay? So we're doing that, so all we're doing is we're just rotating, okay? And then integrating from, you know, minus whatever to plus whatever. So the way we do that, so where this is just applying to the Q naught interval. The other d minus 1 guys we leave alone, we leave them alone, okay? And so the way I denote, or, you know, include this wick rotation is I replace Q naught with I, Q, I'm gonna call it Q sub D, and I don't remember why. I think because of the D dimensions, maybe, I don't remember. Bar, QD bar, okay? And the others, so the other D minus 1 guys, let's call them QJ, they just stay QJ, right? So we don't have to do any rotation on those guys. All we're doing is this wick rotation, this rotation in the, you know, onto the imaginary axis for Q naught. Right? Actually, I think this is a typo, but that's called Q bar. All right, so what does this buy us? Well, it buys us that the magnitude now of Q squared, remember the whole point of this was that we were in Minkowski space, so we couldn't use spherical coordinates. But if I do this wick rotation, then this factor of I, when it's squared, gives me a minus sign, right? So if I computed Q squared, I would have minus Q naught squared minus Q squared. And if I take the magnitude, which is all we worry about in spherical coordinates, this is plus now. So this would be Q bar now. Okay? So the whole idea of the wick rotation is to get us into a spherical coordinate system. All right. So up there we have a d-dimensional integral, right? And one of these is Q naught, so when we do the wick rotation, we're going to pick up an extra factor of I from the integration element. Right? So at this point, let's write down where we are. So I have my integral, a squared. And here's my factor of I that came from the wick rotation, squared over 2, the integral dx, the integral d, now it's QR. Over 2 pi d. And Q bar squared plus omega squared. Yeah, that's right. Okay? So that's where we're at. Now we're in a point where we can start to use spherical coordinates. Now what are spherical coordinates in d dimensions? I don't know. But at least I'm now in a spherically symmetric d-dimensional space. Okay, and just to remind you, I'm not sure why I put this in my notes at this point, but just to remind you, what we're after is computing the self-energy, and then we'll apply those conditions. So our self-energy is, again, I, k squared, minus a, k squared, minus b, m squared. Okay, and when we apply those boundary conditions on the self-energy, we'll be able to extract a and b. Okay, that's the idea. All right, so we want to try to compute this guy. If you're following along in the notes, I'm skipping ahead to slide 26. There's a couple pages in there talking about how you can, well, it's just another way of getting A and B. But let me just show you the more explicit way. Okay, so we want to do this integral. We know that for D equal to 4 or higher dimensions, it's UV divergent, right? And so we've dealt with that those types of divergences before. And there, what we did was what's called a Pauli-Villar's momentum cutoff, or it's the Pauli-Villar's momentum cutoff regularization. And what we did was we replaced our propagator with something that depends on some cutoff. We had to do it in a Lorentz invariant way and all that stuff, blah, blah, blah. Right, but when we replaced our propagator with something that looked like that, and we integrated from 0 up to the cutoff, we get something that's finite. Okay? So that's one way of doing it. And a lot of people would say that's the more natural way of doing it. Because what you're saying is, you're basically cutting off your because we're ignorant of what lies above, lambda. Okay. So cutting off the momentum seems completely reasonable. Okay. All right, but what I want to show you is another technique that a lot of people use. It's called dimensional regularization. Okay. So we're going to use this approach. Okay, so let's see it in action. So let's take this integration element. So let me first consider this d q bar over 2 pi d. And let me write it in d-dimensional spherical coordinates. So it's going to be an integral over some angular part in d dimensions, 2 pi to d, and then the radial part, right? d q bar d minus 1. And if you plug in d equals 4, you can convince yourself that, or d equals, d equals 4. You can convince yourself that it's the normal integration, okay, for spherical coordinates. Okay, so we're going to use another trick in order to get the angular part, okay? Because we know if we can do this part, then we can do this. We know how to do this part. This is just the normal integration, and this thing's spherically symmetric, and we can use all our normal tricks. Okay, but to compute this angular part, you want to use a trick that's not completely clear where it comes from. So just accept it and move on. Okay. So what we want to do is we want to use the definition of an integral of a Gaussian. Okay. So I know that if I integrate dx e to the minus x squared, e to the minus x squared, yeah. This integral is what? Anybody remember?
Square root of pi.
Yeah, square root of pi.
Right.
Okay? All right, so let me take that and let me raise it to power d. Okay? And so let me take this stuff in here. Right? So that's going to give me an integral d dx. All right? And then this guy is going to be exponential, and all those arguments are going to sum. right? So I'm gonna have an exponential and a sum inside. I equals 1 to b, there's a minus sign, xi squared. Okay? Okay. And now, let me transform this into spherical coordinates. So that means here I have integration over the angular part in d dimensions. And here I have left dx next to the d minus 1 from 0 to infinity. So this is the radial part. And then here I've got e to the minus x squared. Okay, because this is just the sum of the individual pieces squared is the radial part, right? What am I saying? The length squared of your vector, right?
Right.
So that's what happens to the sum here, and going from here to here. Okay, so x squared is like x is like the radial part. See what I mean?
Can we only do this because Minkowski space is flat? So otherwise length wouldn't just be like the square of all vectors. Or did the flatness of the Minkowski space come in earlier?
We're assuming here that we're in Euclidean space. Right? That's what we've, because it's gonna, it's corresponding to this interval, right? Here we've already Wick rotated. So that
Right, we Wick rotated the time space so that it would look Euclidean.
Yeah.
So that's where the flatness of Minkowski space
Yeah,
came
yeah,
from?
yeah,
Okay.
yeah, exactly. Okay. All right, so what do I want to do next? So now here I want to do a little, so transform this from an integral over dx to an integral over dx squared. Just for convenience, and I get a factor of 1/2 from doing that. This is integral over dx squared now, x d over 2 minus 1, d to the minus x squared. 0 to infinity. Okay, so just making a transformation. Right? And this thing, here, anybody know what it is? Yeah, it's a gamma, it's what's called a gamma function. Gamma of x, no, gamma of d over 2. Right? And then I still have my factor of 1/2. And here I've got my integral over the angular part. Okay, the important thing is that these are constants now, right? And so now I can solve for the angular part of that integral. Because when I go back to my original problem, wherever the hell it is, it's gone. It only depends on the radial direction, right? It doesn't depend on the arguments. Don't depend on the spherical direction. So I can go ahead and do this integration. The problem was I didn't know how to do it in d dimensions. Okay. So now I can solve for that guy, and what I find is replace this guy with 2 pi to the d over 2 all over gamma function d over 2. Okay? So we're done with the angular part. We never have to do it again. Okay? And just in case you've never seen the gamma function, let me just write down some useful properties. So gamma n plus 1 is equal to n factorial.
Yeah.
Gamma. Did you guys see this in math methods or no?
I maybe I ended up having to look it up online, and I remember it from there.
Oh, okay. So these are useful in, in just, reducing a gamma function. And then this one is particularly useful when you take the limit of small x. Okay? And this is going to be one that we use a lot. It goes like -1 to the n factorial, and then 1 over x minus the Euler-Mascheroni constant plus k equals 1, n, 1 over k, plus order x. So I've expanded here in x, and I'm just taking the leading term, which goes like 1 over x, so we're talking about small x, constant term, and then the order x term, which is dropped. Okay? So that is a useful expression that we'll use a lot. Okay? Because like I said, we're going to compute things in dimensional regularization. You compute in less than d equals 4, and then you take the limit as you approach that. Okay. So that means that we're going to be taking something that's small and making it smaller. Right? And this guy is just a numerical constant. If you've never seen it, it's something like 0.6. I've got 0.577, blah, blah, blah. But for theorists, it's 0.6. Or you can just call it 1. I'm just kidding. All right? Mm-hmm.
Is phi d or d omega d or d omega?
What do you mean? It's the,
It's just omega.
yeah, it's the integration. You mean, is that what you mean?
Or we can say omega d itself, the integration of d omega d itself.
Plus constant.
Yes, integration.
What?
Because you're integrating the differential element,
Right.
and so can't we just call it?
Oh, yeah, that's part, yeah. So you're just saying, okay. Yeah, but what we have in the integral is this. So that's why I'd rather write it like that. Does that make sense?
Yeah.
Okay. But yeah, you could. Okay, so now it's time to put that stuff in. See where we are. Okay, so I, k squared. Let's see, so I've got two factors of g. I've got 2 times 2 pi d. Now here's my stuff from the angular integration. D over 2 all over gamma, d over 2. And now I've got the integration of my Feynman parameter. And then finally, integration over dq bar. This is the radial part, q bar d minus 1 all over q bar squared plus omega squared. Looks right. Okay, so to do this radial part, you want to make a switch from your integration variable of just q bar to q bar squared. Right, so if I do that, I pick up an extra factor of 1/2. This becomes squared. Then I get q bar squared d over 2 minus 1. And that stays the same. Okay. All right, so now you want to make a change of variable. Okay, and obviously, change of variable is going to be omega all over q squared plus omega. Right? I mean, it's completely clear. Okay? I'm joking. And so that means So it means everywhere that we have q bar squared, we can replace with omega over z times 1 minus z. And that means that the differential of dq bar squared is just omega over z squared times dz. Okay, so what is it? Where does that get us? Alright, so that means that the radial integral that we have right here, I'm not going to rewrite it. So this guy becomes, after that change of variable, 1/2 dz and omega over z squared and omega over z to the d over 2 minus 1, and then 1 minus z to the d over 2 minus 1 is z squared over omega squared. Doesn't look like we got very far, does it? Well, let's pull out everything that is a constant outside of this integration. And so I have 1/2, I have omega, I've got to the power d over 2 minus 2, and then I've got the integral dz, z, 1 minus d over 2, and 1 minus z, d over 2. Okay? And it turns out that that integral is also a well-known integral, beta. Beta. Yeah, so this guy is the beta function. So we would, okay, so let me just write. So we would call it b, and then the arguments, I don't remember how the arguments go, but this is what I have written, so I'm going to write it. You have to look, maybe, yeah, I've got it. I've got the definition of the beta function. Well, let me just write it. So the definition is integral from 0 to 1 dz z alpha minus 1 minus z beta minus 1. Yeah, so that's the definition of the beta function in general. Okay, and in general, you can evaluate it, and it's a product of gamma functions. Okay, so that's the beta function in general. All right? But the good news for us is that we've evaluated the loop integral. We're done. Right? We did the angular part, and now we've done the radial part. Okay? All right? And like I said, before you jump up and high-five yourself, just remember that we still have the pesky Feynman integral to do. Okay? And that's the one that, like I said, typically you whittle it down as far as you can, and then you plug it into a computer. Okay? And do it numerically, because it can get messy. All right. So let me go over here and write out what we have. All right, so I've got I integral to the g squared 2 pi to the d 2 pi to d over 2. This is where PowerPoint's looking really good. Integral over x from 0 to 1. And then I've got factor of 1/2, factor of 1 over 2 minus d over 2 gamma, so this is coming from the beta function. D over 2 all over gamma, 2, right? Yeah. Okay, and if I simplify that, I get something, doesn't look half bad. It's g squared, again, over 2, 4 pi d over 2, gamma of 2 minus d over 2, integral over dx from 0 to 1 of 1 over omega to the 2 minus d over 2. Okay, so that's where we are with this integral. No, no, because I changed. Oh no, there's a 2 pi here. Yeah. So I made the change to 4 pi. Yeah. I think it's right. But let me know if it's something wrong with it. Okay, so all that's really left to do now is, well, we want to do this integral, right? Like I said, it's tough. The first thing we have to do though now is we've computed the integral in d, less than 4, but now we want to take that limit and take, take the limit to 4 or higher, whatever dimension we're working in, and extract, the pole structure, the divergent parts of the integral, okay? Because those are the guys that we have to cancel off at the counter terms, okay? All right, so we'll take a 2-minute break here, and we'll pick it up. Do that. All right, so next step is to take the limit as d goes to 4 or 6 or something equal or greater than 4. Okay? Now, there's one technical issue that we need to address, and it has to do with the coupling. Okay? So you guys remember before we really got into this radiative correction or loop correction stuff, we talked about dimensional analysis. Right? We found there that in our phi cube theory, this coupling has a mass dimension of 1/2 6 minus d. Right? You guys remember this? So we worked this out in d dimensions, and this thing is. Oh hey. Sorry.
I was just about to say you.
Right.
I was just about
I
to
don't know
say
why I
you.
thought, yeah, sorry. It's on film, so you can.
It's only like
Yeah,
about
can you do
5
it?
seconds
I'll
or
try to catch
so.
up.
Yeah. So we're just, okay, so let me start back over, okay? So we want to take the limit, right, as d goes to 4. But the first thing we have to do is address this, this coupling, okay? So when we were doing dimensional analysis before we started this section, right, we found that this thing has a mass dimension of 1/2 from 6 minus d, okay? And what else do we have? So it has this mass dimension, which I'm going to define, I'm going to call it epsilon, okay? And I told you guys that it's always desirable to have couplings that are dimensionless. Right? We're going to see why later on. So just hold on. But for now, just accept it, right? That we want dimensionless couplings. Okay? And if we work in d equals to 6, that's exactly the case, right? We have dimensionless couplings, and that's the whole reason that we're going to work in 6 dimensions, or that we have been working in 6 dimensions. All right, but in this dimensional regularization thing, we're taking d away from 6. d is smaller than 6, right? It's smaller than 6 by some factor of epsilon, okay? And so that means that in d less than 6 dimensions, this guy has a mass dimension. All right? Well, we don't want that. We want to keep this coupling dimensionless in all dimensions. Okay? So what we do is we rescale this guy. Okay, we rescale this coupling. And we shift all the mass dimension into a new parameter that I'm going to call mu. So all I'm doing is I'm just, when we work in, in dim reg, our couplings in general become dimensionful, right? And we want them to be dimensionless, right? And the way we do that is to pull out and introduce some unphysical scale. We don't know what the scale really corresponds to. We're just pulling out some thing that has units of energy to the epsilon power.
Is dimension full of what?
I don't know.
And is that epsilon, is that the superscript for the?
Yeah, for mu. Yes.
Okay.
Yeah. Yeah. So that, so this thing has, you take the mass dimension of this, it has mass dimension of epsilon.
Right, okay.
Okay? All right, so everybody cool with this? Yeah, okay. So the whole idea is we want to keep we're working in 6 dimensions normally, right? But when we're in the world of loops, we have to kind of meander away from 6 dimensions. And when we do that, we want to keep the coupling dimensionless, okay? All right, so what do we do? All right, so let's use this expression, right? So what we're going to do when we take the limit of d goes to 6, we're basically taking the limit of epsilon goes to 0, right? So let me use this guy right here to write d, and d is, if I do an algebra right, 6 minus 2 epsilon. Okay? So this is the dimension that I want to plug in into our integral. Okay, I want to plug that in and then take the limit of epsilon goes to 0. Okay? So what do I have? So if I do that, I'm skipping some of the algebra, I get g squared 2, I get 4 pi cubed, I get 4 pi, sorry, in my notes I call this mu twiddle. Let's see why I'm not. This is mu twiddle squared to the epsilon power gamma minus 1 plus epsilon in my integration dx omega and then 1 over omega to the epsilon. Okay, so this is what I get when I plug in d equals 6 minus 2 epsilon. And I simplify all this stuff, this is what I end up with. Is that right? I'm just kidding.
D equal
Think so.
So I plug in d equals 6 minus 2 epsilon into here. So I can see that I can get the 4 pi cubed. Right? I get a factor of 4 pi to the minus epsilon. So that gives me, where am I? I got lost. Wait. I'm going from, oh, going through. Yeah. So this is the 4 pi epsilon. This guy came from the fact that I had g squared. So on. Okay. All right. So we have, at this point, we've got the self-energy, and let me write down what it is. So first I'm going to introduce the what we call a reduced coupling. Call it alpha. We said equal to g squared over 4 pi cubed. Okay. This is in complete analogy to the electromagnetic alpha. Okay. And so what I have so far is, let me put everything together, g squared. What do I have? I've got alpha over 2, 4 pi, mu twiddle squared to the epsilon, gamma to the minus 1 plus epsilon, times the integral, omega, and then I've got my counter terms coming in at minus ak squared minus b m squared. Okay. So we know the integral is going to be divergent, but we're going to tune a and b to cancel those divergences exactly. All right. So what we want to do is now we want to take the limit of epsilon goes to 0 for that stuff. I've got this. Okay. And to do this, we're going to use that expression that I'd written earlier. So we're going to use this for this guy, minus 1 plus epsilon. Right? We're taking epsilon to 0. And so this guy is approximately minus 1 over epsilon minus gamma plus 1. Right? That 1 over k s went away. Okay, so this is what we have. To leading order, or to, I guess, non-vanishing order, right, for epsilon. All right, so we do that. That's what gamma is. And then anything that goes like 1 over, or it goes to the epsilon power, we rewrite it using a little math trick. So we have something that's to the plus or minus epsilon. Right, so we can write that as exponential natural log of a plus or minus epsilon. All right, and then the natural log lets me pull this out as an exponent, I mean as a prefactor, right? Plus or minus epsilon natural log of a. And then we can expand this guy as epsilon goes to 0, and it says 1 plus or minus epsilon natural log of a. so this is just the usual trick that we use in taking this limit. All right, so you're gonna see some natural logs popping out of some stuff. Okay. All right, so what do I have for the interval? So I've got I, k squared, minus alpha over 2, and we got 1 plus epsilon natural log 4 pi mu twiddle squared. And then I've got a factor that goes like 1 minus epsilon, 1 over epsilon minus gamma Euler plus 1, and then my interval. So I've expanded this factor of 1 over omega. Get something that looks like that. Okay. Okay, I can pretty this up a little bit. I can rewrite minus gamma Euler as natural log e to the minus gamma Euler. All right, that's going to let me pull it into that factor with 4 pi mu twiddle squared. What else can I do? Yeah. All right, so let me do that. All right, so I have k squared, and I've got minus alpha over 2, and now I'm pulling everything inside the integral. Dx omega 1 over epsilon plus 1 plus all this stuff that gets grouped into natural log. Natural log 4 pi mu twiddle squared e to the gamma e omega. Okay, so taking the limit of epsilon goes to 0, expanding everything using this trick of writing the Euler constant to group it into that stuff. Okay.
I don't think we have any of the terms that we started out with the left. I think they've all been turned into new terms.
Yeah, that happens. That happens sometimes. Okay. What we can do is we can define a new mu, NEW mu, to pretty it up even more and to get rid of another thing another constant that we introduced. So let me define mu to be square root of 4 pi e to the minus gamma e over 2 times mu twiddle. All right, it's just a constant, and so we can just shift stuff into it. We don't really know what it is, right? Some energy scale. It's an unknown at this point, so we can shift more crap into it, all right? And what that does is it lets me at least get rid of some of this stuff, and I get something that looks like just mu squared over omega. Okay, so I don't have all those 4 pi's and e to the Euler constant crap floating around. Okay? All right, so the good news is we can do this integral, right? Remember, this thing just goes like x squared, right? So I can do this integral. It's an integral from 0 to 1, okay? What else do well, let me write it. Let me just finish the calculation and we'll look at it. All right, so if I do that integral, I get minus alpha over 2. I get 1 over epsilon plus 1. I get k squared over 6 minus m squared. All right, that's coming out of that omega when I plug back in what capital omega is. But this integral, the natural log one, is still a pain, so we're just going to leave it alone. So what? So we're interested in the epsilon goes to 0 limit, right? And what we see is the divergent behavior now is kind of signified in that 1 over epsilon term. All right, so that's our pole, that's our UV divergence. Okay? And so what we're going to do is we're going to use the counter terms along with those boundary conditions on the self-energy to cancel off those poles, or that pole. Okay, everybody with me?
Think
I know
so.
I know there's been some crazy steps here and there, but you get the idea of where, you know, we started with that loop integral.
Yeah.
We had to introduce Feynman parameters. You know, what else did we do? We combined the denominators. We went through some stuff to, you know, did a Wick rotation to get the integral into a spherical, you know, spherical coordinate system. Then we used the trick to compute the angular part, right? And then finally we did the radial part. And then finally, we took the limit as we approach 6 dimensions, right? Okay, so repeat that back, Michael. All right, so we're here. So we've got the integral. We've gotten where we want to get. Okay, so this thing, if we really wanted it, we could, you know, toss it into, you know, Mathematica, or, you know, you could, whatever. You can compute it numerically. Okay, but the important part is that we've extracted the pole, right? We've extracted the divergent behavior. Okay, so now what we want to do is use those counter terms to cancel the poles. And that reminds me of a story. When I was in grad school, my wife woke me up one night. She's like, "Chris, wake up, wake up." And I was like, "What's wrong, what's wrong?" She said, "You were screaming in your sleep." I was like, what? I said, "What was I screaming?" She said, "You were screaming, I have to cancel the poles. I have to cancel the poles." So, but I did this, you know, this loop stuff. I did it for a living during grad school and first couple of years of postdoc. So I was under a lot of pressure you know, to cancel the poles, I guess.
Did she have any idea what you were talking about?
No. No, she was clueless. Okay, so what we want to do is we want to plug that into the expression that we have for the self-energy. And we want to use these boundary conditions that when we set k squared equal to m squared for the self-energy, and when we set it for k squared equal to m squared for the derivative, both of these guys vanish. Okay, so this is where you have a choice. Okay, we have a choice of what we use A and B to cancel. Okay, we could use A and B to just cancel the poles. I mean, that's what we put them there for, right? But we could also use them to cancel off anything unphysical that we might have introduced along the way. Okay, so that's what we're going to do. All right, so in particular, so we want to cancel off this pole because that's obviously unnatural, right? But the other thing that we introduced that was kind of unnatural was this scale mu. Right? So what I'm going to do is I'm going to rewrite this natural log again. So it's mu squared over omega. And what am I going to do? I'm going to multiply top and bottom by m squared. And then use the property of the logs, and it's going to give me natural log mu squared over m squared minus natural log of omega over m squared. And I'm doing this because when I use those boundary conditions, I want to cancel off the mu squared behavior, right? And I had to pull it off of this guy because it was being integrated over, right? Right up here. Okay, so that's why I'm going through this rigmarole here. Okay, so now this thing is just a constant, it can come out, and I can cancel it off with the counter terms. Okay. All right, so that's just some bookkeeping. So my self-energy now looks like this. We get alpha over 2, dx 0 to 1, omega, natural log omega over m squared. Okay. And then when I group factors, so I want to group factors of k squared and factors of m squared together. Okay. So k squared, I've got the contribution from the loop, which looks like alpha over 12. Is it? It can't be alpha, right? It's supposed to be just 1 over 12. Oh no, I think about it. Yeah. No. Oh yeah, this is not. It's 2 separate terms. What am I doing? Okay. So I got alpha over 12, 1 over the pole, plus natural log mu squared and m squared plus 1 minus a. So here's the contribution from my counter term. Remember, a multiplies k squared. And then I've got minus m squared. Here, I've got minus alpha over 2, 1 over epsilon, plus natural log a squared over m squared, plus 1 minus b. Okay. And like I said, we're always free to choose A and B. Okay. Obviously, we want to choose them to cancel off poles, but we don't know what the scale is. Right? So we could also use the counter terms to cancel off that scale, if we so wish. All right. So in other words, let me just define. So we want to kill off this stuff. Let's kill off that stuff, and then we'll also kill off those constants. Those ones are basically the alpha over 12. So let's just define A to be minus alpha over 12, 1 over epsilon.
Shouldn't that be 3 lines since it's defined? The A.
Oh, no, I'm just saying we're choosing, so it's bad.
Oh, okay.
Bad terminology. We're just choosing A to be this. M squared plus 1, and then plus some constant piece, which we'll determine using the boundary conditions, because we haven't used those yet. All right. I'm just choosing A and B, such that they cancel off these guys. So this is plus alpha over 2, 1 over epsilon, plus natural log mu squared, m squared, plus 1, and plus b. Okay, so these are numerical constants that we're going to determine. All right, so once I do that, my self-energy is completely finite, and it's free of any unnatural scales. We just have self-interval to do, plus alpha, and this is k squared over 6 times kappa A minus kappa B squared. That's it. Oh, okay? All right. So all we have left to do now is to determine these kappas. So we're allowing A and B the freedom to have some extra numerical, additive pieces, some constants. But we can determine them using our Okay, so, yeah, so the point is, the next thing we wanna do is determine these guys, but it's gonna depend on this integral, right, our final answer, because we're gonna have to do that integral to get the numbers out and then apply the boundary conditions, okay? So at this point, it's probably better just to resort to a computer, okay, if you want to determine what kappa A and kappa B are. So this is one particular choice of how you can cancel off, you know, or how you can renormalize. It's a renormalization scheme. There's different schemes, so you can choose to just cancel off poles. You can choose to just cancel off poles plus this stuff, or you can do what we've done, which is choose to kill off, you know, the pole, some natural log pieces, and or some unnatural scale pieces plus some constants. Okay. I've got the answer. It's not that enlightening though. So I'll let you look at it. So I evaluated this integral, and you can actually do it. It looks like in closed form. Okay. So it's not that tough. You don't have to do it, but I probably had to resort to Mathematica to get it done. I'm worn out. Let me just stop there, and then we'll pick it up. So we're done with the 2-point function. So we've completely determined our counter terms to this order, right? To order g squared, or order alpha, okay? And so we've got our counter terms, and now we want to move on and talk about the 3-point function, all right? The vertex, okay? Corrections to the vertex. And it's going to follow the same path. You know, the difference is our diagram is going to be a little tougher because the loop diagram we're going to have to compute is going to look like this, the triangle diagram. Okay, so we're going to have 3 factors of denominators, or propagator denominators in our loop. Okay, and so there, it's going to get messy, but we follow the same path. Okay, so I'll take you through that calculation on Tuesday. Okay? Any questions? I'm going to go back to my office now and type up the midterm. I've got it in mind. I just have to put it on paper. Okay? And then I'll share it with you.
So
okay?
maybe tonight?
Yeah, it'll be there tonight. It's the latest. But I'll send out an email. I'll let you know. Yeah.
If you have it, maybe you can post the Mathematica equation that you used to evaluate it.
What?
So you already evaluated that integral?
This?
Yeah.
It's in the
notes.
talk. Yeah. The answer is. Yeah. But yeah, no, the Mathematica notebook that I did that is probably long gone. I gave up. You know.
Oh, you
I went cold turkey on Mathematica, so I'm not.
You did a while ago.
Oh yeah. Yeah, I don't use Mathematica anymore, so. But anyways, all right. So I'll do that, and then you guys let me know when you run into problems. Okay. If you have questions about it, there's something not clear. You know, don't be afraid to let me know or to ask. Okay.
Okay.
All right.